In this video, we're going to look at laws of exponents. Let's take a look at our 6 basic properties of exponents here. If s, t, a, and b are real numbers, keep in mind that a is greater than 0 and b is greater than 0 as well. In these examples, I'm going to give some numbers also just to help clarify some of these properties. In these cases, maybe I might actually assume that, let's assume that s is a value of 2 and t is a value of 3, just to make things easier. So if we have let's say a to the power of 2 times a to the power of 3, in a way you're saying let's have a times a, and then we multiply that by a times a times a. Well, we see here that there's a total of 5 a's, so we have a to the power of 5. If we just think about it in general, what we're doing is we're taking the power of the first term, a to the power of s, and we add that with t, right? S plus t. That's how we're getting that 5. 2 plus 3 gives us 5. Similarly, if you see parentheses, a to the power of s means you have, let's say again, that s is 2 and t is 3. So we're like having a to the power of 2 3 times. It's to the third power, right? And so this is saying a squared times a squared times a squared. Well, that's a times a times a times a times a times a. So that's a to the power of 6. Okay, so if you think about how we get the 6, it's like multiplying the s times the t. So another easy way of thinking about this is because you have parentheses there, that means you want to multiply your powers together. Similarly, for number 3, again, you see parentheses there, so you're kind of in a way multiplying that power, but in this case we're distributing. So we're having a to the power of s times b to the power of s. To show why we do that, we can expand it. If you have a times b, s number of times, again, let's think of s as 2. Okay, so if we have ab squared, it's like saying a times b times a times b. And using the commutative property of multiplication, that's like saying you have a times b times b. So you see that's why you have 2 a's and 2 b's. So you can see how you just distribute each of the powers to those terms inside. Number 4, this is like saying 1 times s number of times, right? Well, that's just going to give us 1. A to the power of negative s, what does negative mean? Well, hopefully from a previous course, Algebra 2, you remember that a negative exponent is really the same as a 1 over a to the power of s. And if you have that parentheses around there, you can also distribute that s to each of those terms, so you would get 1 over a to the power of s, like that. And then anything to the 0 power is the same thing, the equivalent of 1. All right, let's do some examples. Let's try number 1 here. So here I see 2 times x to the negative third power. So what we can do is distribute that negative 4 to everything in parentheses. We get 2 to the negative fourth, x to the negative 3 times negative 4, which will give us a positive 12. So one thing to note is that these two items are separate. You have 2 to the negative 4, which is really the same as 1 over 2 to the power of 4. And then you also have an x to the 12th off on its own. Keep in mind that the 12 does not have a negative attached to it, so you do not bring that x over on the bottom. You do not do its reciprocal. So x to the 12th actually stays put where it is, which actually makes it still a numerator, and then the 2 to the 4th, which is 16, becomes the denominator, like that. Let's do another one. Let's try number 4. Now, oftentimes what I see is a very common mistake is that because we see the parentheses here, we would want to distribute the negative 1 to each of these terms. So what I end up seeing people do is they end up getting x squared plus x cubed. Okay, well, this property actually doesn't work. To take a look at why it doesn't work, you can just imagine a more simple case. Let's say a plus b squared. If I did that, would I distribute that 2 to each of those? Would I get a squared plus b squared? You know that's not right. That's a binomial squared. This is actually giving you a squared plus 2ab plus b squared. So you obviously cannot distribute that exponent to those terms if there's an addition in the way. one thing we had talked about in our properties of exponents was that it only works if you have multiplication, if it's a times b, not a plus b. So be very careful with that rule. Okay, so what do we do instead? Well, you do see lots of negatives. What you could do is think about what negatives mean. What this is the same as saying is, I'll work with this -1 first. It's the same thing as saying 1 over, we're doing the reciprocal, 1 over x to the -2 plus x to the -3. Now let's work with the negative exponents on the denominator. What this is saying is 1 over x to the -2nd power is the same thing as 1 over x squared plus x to the -3rd power is the same thing as saying 1 over x to the 3rd. Okay, so now we have our fraction a little bit more simplified. Now what we want to do is think about how we can work with that denominator. We have 1 over. Now how do you do 1 over x squared plus 1 over x cubed? Hopefully what you see is that you are adding fractions of unlike denominators. And because they are unlike denominators, you know that to add fractions, you need to have common denominators, which means the first fraction needs x cubed on top and bottom, and the second fraction needs x squared so that you have common denominators. So what do we end up having now? Well, we now have x cubed plus x squared all over the common denominator of both of them, which is x to the, how do we do x to the 3rd times x squared? Remember your properties of exponents? X squared times x to the 3rd is going to mean we add the powers. So we have x to the power of 5. Okay, so what we have now is 1 divided by a fraction. I'm just going to write it off to the side here. If you ever have 1 divided by a fraction, another way to think about that is 1 divided by a fraction. Another way to think about that is division is multiplying by its reciprocal. Okay, so taking that idea, this is now going to turn into x to the 5th over x cubed plus x squared. And there's going to be your final answer for number 4. Okay. All right, let's take a look now at another problem. Let's do number 7. Let's just go down the column here. All right, so what do we notice here? We have a cube root, meaning we're looking for groups of 3. Okay, groups of 3. And anytime we have a group of 3, we can actually pull it out of that cube root. Let's see what else we have. I notice that we have a 125 as a base. I also see we have a 5 as a base and a 25 as a base. Well, all those numbers actually have something in common, right? They all have a common base of 5. So we'll just rewrite this. This is the cube root of 125 is the same thing as 5 cubed, and then that is to the power of n, times 5 to the power of 4n, all over 25 is the same thing as 5 squared to the power of -n. Now keep in mind, when you have a power to a power, this rule tells us that we can multiply them together. Power to a power means we can multiply. So simplifying this, I have the cube root of 5 to the power of 3n times 5 to the power of 4n divided by 5 to the power of -2n. Well, they actually all have the same base of 5, so a property we can use is if they have the same base, we can actually combine them together as one base. What will that become? Well, we add these powers up. So we have 3n plus 4n. So we have 5 to the power of 3n plus 4n. And then we also have a same base here of 5, which means we know, because it's division, you subtract that power. So we're going to say minus a -2n. So let's combine all that together. Okay, so what we now have is the cube root of 5 to the 4 plus 3, 7n, plus another 2 is 9n. Okay, there we go. And then since we have a cube root is technically the same as to the power of 1/3. So why don't we just change that into 5 to the 9n to the power of 1/3. That's what the cube root means. And then if we combine those exponents together, we get 5 to the 9 divided by 3 will give us 3n. So we have 5 to the power of 3n, just like that. Okay. All right, we'll stop our video here because that'll conclude our laws of exponents.